Okay, let's get started again. So this is the last lecture of the second mini course, Farbod. Who's going to put everything together?
Thanks everyone for coming to the last lecture. Since at the end I'm probably going to be rushed, I want to thank the organizers for including me in this wonderful program, and thank the audience for being very engaged this week. I was very happy to see, at least in the yesterday and today, many of the objects that I introduced were actually used by other speakers, so it wasn't a completely irrelevant set of things that I've been talking about. So my plan is to put everything together, meaning that I'm going to give a few theorems that relates height theory, Berkovich spaces, tropical quantities together. Before doing that, at the end of last lecture, I just introduced the distributional Laplacian for, say, graphs, but I had made this claim that it's the same as electrical network. I didn't do that. So let me very quickly say, what do I mean by that claim? Because later on, I'm just going to do some electrical networks as well. But in fancy terms, it's going to be potential theory. So let me, so there is this delta distributional Laplacian, which goes from the piecewise linear functions, continuous piecewise linear affine functions on a metric graph to discrete measures of total mass 0. Gamma is a metric graph, which is supposed to be the skeleton of the Berkovich space for me. I want to say something about, so when you do analysis or potential theory, you want to solve so-called Poisson equation, or one of the things that you would be very interested in is a Poisson equation. You want to find a function which, if you apply Laplacian operator to it, you get a assigned measure of degree 0. So this is a fundamental problem, Poisson equation. Discrete measure, yes. I'm going to do right now an example. And there's a fundamental solution that you might want to do. In fact, another word that was used yesterday, you might think of this as a Green's function. Okay, this is a little bit more general than the classical notion of Green's function, but this is very common terminology in Arakelov geometry. That you want, essentially you want something, maybe an easy measure here, and find something. So Laplacian is not invertible as an operator, but it might have an integral kernel, and you want to compute that. So Green's function helps you solve this kind of differential equation. And I'm going to, so my goal is to show that this is really electrical network problem on graphs. So let's say, so example. Let's say I take delta of f equal to delta measure at y minus delta measure at z. And so this solution is going to depend on y and z. I'm going to call that solution maybe j sub z of a variable and y. So the function, it's going to be a function of this dot. Because I've fixed the y and z, I want to incorporate that y and z in my notation as well. I claim this is precisely the solution to the following. Well, I don't claim, it is. I will just state it to you. It's the solution to this following electrical network problem. I'm going to explain in a moment what I'm doing. So I'm going to put a battery, which is a source of current, not source of voltage, not the battery that you buy in grocery store, but multiple $100 battery that fixes one amps of current going into your network. This is your network gamma. So that's the plus delta y. Minus delta z, the current is coming out here. And then this network is going to get warm. It's an electrical network, resistive electrical network. All these lines in my network are considered to be copper wires. The longer a line is, the more resistance that line has. And then what I'm computing is precisely the potential difference between the point x and z. And this notation means that, so this is only well-defined, there is a one-dimensional kernel. Laplacian of a constant function is 0. So I have to make a choice. I've made z to be 0 potential. And potential is what I'm computing. So you can imagine in a concrete example, you can actually do Kirchhoff laws and compute all sorts of things. OK? And this is a fundamental solution because it's sort of any other measure can be decomposed into this kind of measures, and you can give formulas for them. And maybe, OK, this was mostly conceptual, but one thing that I will probably use if I have time is the notion of effective resistance, so definition. And this will come into some computations of heights. R of y comma z, it's going to be the diagonal. It's going to be jz of y comma y. By that, I'm saying something that I hope you remember from physics, very basic physics, that voltage is resistance times current, and the current is 1. And I'm saying the potential that I will have, the voltage difference between y and z is going to be precisely R, the effective resistance between y and z. OK, so this is a fancy definition, but it's really the definition that if I have this graph, if I tell you this is x and this is y, and what's the effective resistance between x and y, the parallel law says this is going to be, the inverse of that is going to be the summation of the so-called parallel law, the summation of inverses of resistances. So you compute R. What's that? 3/2? Or something like that. OK, so that was a very quick, hopefully, justification of potential theory in this one-dimensional case is not very different. And in fact, this distribution Laplacian is closely related to the usual Laplacian in graph theory that you might have seen in the edge-weighted case. If you decide that I only care about these 10 points, you can actually make a 10 by 10 matrix. It's Laplacian, and then you can do these things linear algebraically. You don't really need analysis. OK. Now, putting things together. Any questions about this? Finishing up from last time? Yes. This is voltage. This R? This R is this R. So this is called effective resistance. Did I answer your question, or you're saying something?
Because on the left side you have to the minus 1.
1 divided by so this is parallel law. Oh, you're saying that my computation is wrong? Oh, OK. You really wanted to embarrass me. I'm teaching, actually, adding fractions to my 8-year-old son. I hope he doesn't watch this video. Any other corrections? OK, so heights and non-Archimedean geometry, but let's for it's really it turns out many interesting phenomena happens at the level of skeleton. So you can safely call it tropical geometry, even though the tools and the proofs you really need the Berkovich space to get to that point. And then you get lucky things happens at the level of skeleton. So recall, I had one motivating example for heights, namely, I introduced the global height, and then I said Néron proved, using the technology of Néron heights and Néron models and so on, that it can be decomposed up to a universal constant, which I tried to call it kappa. For P not in the support of D. And I said vaguely this should be thought of as some kind of a distance to the support, but I'll make that more clear. So I'm going to give a modern description of this, which in particular generalizes the work of Tate in dimension 1 to all dimensions, and it also gives hints about what this kappa should be. I don't want to dwell too much on all the things we can prove, but I want to give you a feeling about what type of mathematics goes into it. And I'm happy to chat more about more details later. And that's not the only example that I want to do. That's why I decided not to give too much details here. So for me, now I'm going to be here for the next few minutes. I want to fix a place. So for me, I want to have a field which is supposed to be my completion. And the Berkovich space that I will work with will be over algebraic closure, completion of algebraic closure of this. But I want to compute heights over F. I will state the result a little bit more general looking. So R is a complete DVR. And then F is the field of fraction field. But this is really the example I have in mind. And then I will make sure that value group is C. When you have a DVR, you have to fix a uniformizer and decide what's the valuation of that uniformizer, the generator for the, and I'm saying I do the right normalization. Not super important. Then I have an abelian variety over F, KV in this case, abelian variety. Then I fix, so the data going into this is also a divisor or equivalently a line bundle. I'll fix a section of that line bundle. S is a global section of L, whose divisor is the D that will go into the height machine, to the canonical height. And then I said briefly, and it was mentioned also in Martin's discussion in open problems, that putting metric on line bundles is an important thing you do for computing heights. I'm going to endow this line bundle with a so-called canonical metric. On L. So I'm going to actually give you a definition, but the fact that this definition actually has a solution is a theorem due to Zhang and Gubler. But the definition is that, remember, this L was symmetric. This D was symmetric. I decided to work with the symmetric theory during this week, which means L is symmetric, which means the multiplication by n pulls it back nicely. So you have a isomorphism of line bundles, which is pulled back by n, or let me just fix 2 as I did for the Tate trick. Gives you an isomorphism line bundle L4. I wrote this for divisors in the past. Multiplication by 2 was pulling back to 4 times the divisor. Now it's the line bundle version of that. So canonical metric is a metric that makes this isomorphism into isometry. So you put metric on each line bundle, and you insist that this isomorphism should be isometry, meaning that takes the metric. And then you check that such a metric exists. And in fact, to do that check, it's very closely related to Tate's trick. So you do a limiting process. That's one of the proofs of existence. So making this isomorphism isometry. Then I'm going to talk now about Berkovich spaces. So everything so far is algebraic, but now I'm going to analytify. So let me just say all analytifications will happen over sufficiently large. So I algebraically close my field and then look at the completion of that. In my running example, this might be called CP. It's the analog of complex numbers. It's a big field that some of the subtle things that you have to worry about disappear. You have a nice uniformization and so on and so forth. OK, now I'm ready to tell you a bunch of concrete things. You look at minus log of norm of S as a function on an analytification of A. But section is going to be 0 when you're on the divisor. That's how divisor is made. So I have to remove something suspiciously familiar. I have to remove the support of the divisor. And this is a metric. It will, I take logarithm, I get a real number. It turns out, so there's a theorem already from early 2000s due to Chamberlain and Toulier. And the way that I'm stating it requires a little bit of explanation, so plus epsilon, but no essentially new ideas. That says this is indeed a Green's function. I won't define Green's function, but you saw a version of it yesterday. I have given you a very sort of elementary Green's function. These J functions were Green's functions. So the statement is that this is a Green's function, meaning that its Laplacian appropriately done is a measure which can be handled. Think of Green's function like nice function, which is good for computations. So this minus log is a Green's function on Berkovich space. And in fact, so that epsilon comes here. This is really the function that extends this thing I'm interested in to the entire Berkovich space. Extending, OK, in the running example that I'm working with, the CP, extending lambda d to an. So lambda d was only on k points, but now it's going to be on the entire Berkovich space over the base change. If you restrict yourself to the original points, you're supposed to get back the value of the local canonical height. Okay, so that's a very nice result, which means that this summation is a summation over Berkovich spaces restricted to classical points. OK, I'm going to, OK, this is a very nice conceptual result, but actually, one other thing is when I defined this, I said it's a continuous function. And I said that's a weird statement. You might want to think about it. It was a continuous function from v-adic points to real numbers. So what does that mean? It means it should pull back open sets in the real topology to open sets in v-adic topology, which back in the 60s would be a weird thing to say, but it's a strong hint to Berkovich spaces, because Berkovich spaces are exactly pulling back real topology to this V-adic spaces, to this non-Archimedean spaces. So that was a hint for sure. But what I want to say, which I don't think I've said any theorem of mine, finally I'll say a theorem that we can actually say what this thing is in very concrete terms in terms of tropical geometry. So I'm going to cheat. There's a definition of a theta function that is quite involved, uses the entire machinery of Raynaud that I mentioned last time and you don't remember, plus things that I didn't say. But my cheat is I'm going to call a theorem a definition. I have this function on the entire Berkovich space. I'm going to restrict it to my skeleton. Remember, skeleton was some real torus. And I'm going to give it a name, f-trop. This is not how we define it. This is a theorem, and in fact, it's more or less a bad cheat, because once you know this fact, many things become obvious. So, but orally, I'm going to say how we construct this. You have a section. So this is for experts. You have a section of the line bundle. It gives you a theta function on the universal cover. So you remember that. It's a non-Archimedean theta function. And then you can tropicalize it, which gives you a function on the skeleton. So let's call that f-trop. You record this information. And then you restart. You have this polarization data that gives you essentially a non-Archimedean version of Riemann form, some kind of a bilinear form, let's say, which I briefly mentioned. There was this bracket that you would get, bracket product that you would get from your polarization. That bilinear form has a quadratic form. Any bilinear form gives you a quadratic form. And you tropicalize that too. And you get something which we would call C-trop. This is the quadratic form. And then you add them, and this turns out to be a function. This was only defined over universal cover. This is a quadratic form. It turns out this will be well defined on the skeleton. But to make this precise, I needed a lot of Faltings-Chai stuff that I don't want to do in this or any lecture. But this is a function, and I will justify this is a very well understood function in cases that you might care about, combinatorially, which is defined over the skeleton. And now I can state a theorem. Actually, the notion of Néron model was mentioned multiple times yesterday. Let me say a definition, which is not, again, a construction. If you have abelian variety over this field, well, you have a map from spec F to the ring. And you might wonder, there is a push forward or not, and the answer is yes, and that's called Néron model. And the fact that this is a push forward gives you Néron mapping property and so on and so forth. So this is going to be the notion of Néron model. And as I said, Néron actually constructed this for height purposes, but it's been used by people that don't care about heights all the time. Okay, now I have everything for my theorem. This is a theorem with Robin de Jong, which was put on the archive, I think, almost exactly a year ago. It's called, the paper is called Local Canonical Heights and Berkovich Skeleton, or maybe Canonical Local Heights. We couldn't make up our minds which one goes first. Canonical, local, or local canonical. So theorem with Robin de Jong at Leiden. Which says this. Local canonical height, which is the, we already said that this is a new, this is Chambers-Loat 2EDA plus epsilon. So P is now an f points minus the support. It's going to be, so you shouldn't expect that I write a formula which is entirely on the Berkovich space, because my Berkovich amplification is actually over the completion of the algebraic closure. It turns out this quantity is actually sensitive to the field that I'm working on. There is a contribution that is on Néron model. It's essentially some intersection number on Néron model. Which, this is x, sorry. So you have x, you look at the closure in the Néron model. You have D, you also look at the thickening, so-called thickening on the Néron model. You have two things and you can intersect. So this is intersection on Néron model. And you have this contribution even if you have good reduction and your Berkovich spaces is not interesting. So this is kind of, I can't get rid of it. But then the theorem says the other data comes from precisely this f-trop function, which I still owe you a. So f-trop of what? You remember you had the canonical tropicalization map. So you have to tropicalize the point that you care about, bring it to the skeleton. Then you have a function on the skeleton that you can use to compute this number. OK, so intersection contribution and this contribution. Let me say, because I don't want to spend too much time on this, this strictly generalizes the Tate's computation, and also it's the correct analog of Néron's computation in the Archimedean setup. In the Archimedean setup, of course, the uniformization and all the theory existed for complex abelian varieties, and he had formulas in terms of theta functions and intersection numbers and things like that. This is sort of the, it's not a direct analog. You can't stare at that formula and you see this, but this is the correct analog. OK? There are theta functions in this formula. But one thing that I owe you is what is this f-trop? I'm pretending this is very explicit, but I haven't given you an explicit thing. So I guess I hope you trust me that this description is very tropical and one can actually compute these. But I'm going to say the computation in the case of principally polarized case is actually quite clean and beautiful. In principally polarized case. By principally polarized, I mean you have a line bundle whose space of global section is one-dimensional, for example. Jacobians are principally polarized. Elliptic curves are principally polarized. Another way is you have the natural polarization map between A and A dual is an isomorphism. There are many definitions in the case of abelian varieties for this. And this is a very well-studied and important class of abelian varieties. And the answer is the following. So I have a sigma, which is a vector space modulo a lattice, which I chose to be x and xr and y. So think of this as some vector space, which is the board in today's lecture. And you have some lattice, which is a z module plus some bilinear form on it. Polarization gives you a bilinear form. I'm sorry, the lattice doesn't. Maybe I should just get rid of the lower. It's supposed to be a periodic picture. So I'm going to, on this, I'm going to define a function called theta. It has to do with theta, but it's not quite f, which does the following obvious thing. It's quantization function. So you give me a point in the vector space. I'm going to find the closest lattice point, and I'm going to remember the distance. That's the function. For some reason, I'm going to remember the square of the distance. So theta of z is going to be minimum, or infimum. It turns out to be minimum of z minus lambda, comma z minus lambda, where this bracket was the bilinear form coming from the polarization over all lambdas in my lattice y. The closest lattice point, or distance to the closest lattice point function. And this function is actually, okay, I've been telling you on the universal cover how it works, but it's a periodic function. If instead of this point I give a shift of it, you get the same number. So it's really a function on the skeleton to real numbers. And very quickly, there's a little bit of a footnote. This function is that. But of course, I wouldn't have called it differently if it was exactly that. Up to a shift and a constant, it's that. So the theorem, let me write it up here. There exists some, what did I call it, A? Yeah. There exists some A in sigma. Actually, we can say exactly where it is. In fact, we give it a name. It's called tropical theta characteristic. And some rational number in Q such that F trop, which I have given some indication it's computable. Here is a computation for the case we care about. Is up to a translation by A is that, and then you have a universal constant. And remember, all these things were well defined up to constant anyway. So it's a good question to ask how to fix this constant, but don't be bothered by this. This actually bothered us a lot because we wanted our formulas to match what Tate had done in the case of dimension 1. And there were some weird shifts that we couldn't understand. So we actually suffered a lot to figure out what this shift is. But now we have convinced ourselves, and hopefully the readers of the paper, this must be there, and it has a good reason to be there. So I want to end this example and do a little bit more fancy heights for the remainder of the time, but let me just say this generalizes Tate's dimension 1 computation. And also, not only it does that, it gives conceptual meanings of some normalizations that he had done, which was not clear what to do in higher dimensions. So just without too much details, it gives, so by normalization, I mean you have to fix constants. These things are all only well defined up to a constant. Here's a proposal. Maybe the constant should be in such a way that the integral of the of this thing over the skeleton should be 1 or should be 0. You have now, because you talk about skeletons of Berkovich spaces, you have now geometric things that you can do. In dimension 1, you have to actually be more clever. It turns out there are natural normalizations that actually matches Tate's normalization, and it makes sense in higher dimensions, which means it gives a local global formula with meaningful constants. By that, I mean you, at every constant, at every place, you make a choice that I want the integral of something to be 0. And then you add all these after you made this choice. So you have a summation. You have the God-given or Tate-given canonical height globally. And you ask my summation and Tate-given summation, what's the difference? It turns out we can exactly say what the difference is in terms of another height. Sorry for the wait.
So this is true for any L or for a particular choice of L?
For this paper, for this talk, I focused myself on symmetric effective.
But for any symmetry, you get the same formula. So
Yes. Yes. No. This is principally polarized.
and then you're taking as L the this polarization.
This is principally polarized again. But even if it's not principally polarized, this construction, if you go through our thing, you can actually, you have a method of writing down what this function is. It's just not so clean, and we are not super motivated to do all the formulas, but I hear Chaboty people might care about it, so luckily Robin is in the Netherlands and Chaboty is everywhere. Hopefully somebody will talk with him to see what they need and we'll compute it. In principal polarized case, it's particularly nice and convincing, and certainly for my remainder of the talk, this function will come up again, so I wanted to write it down. Other questions?
I have one. I can't remember the place B. Is it finite or infinite or anything?
So I have been focusing on the finite place because I've been doing Berkovich spaces, and that's kind of the new part. For the infinite place, already Néron in his 1960s paper gave a similar look, not similar looking, but the right formula of this form in terms of Riemann theta functions, instead of this kind of tropical theta functions. In terms of Riemann theta function, you can find it already there. Well, it's probably better to look at Henry Silverman book on Diophantine geometry. It's written down in terms of the Riemann theta function.
That was my next question.
Yeah. Okay. Now I want to do similar math, but in a way, if I was actually right now, if it was top of the hour, I would say that's all I had to say because it's a good stopping point, but I have 20-something minutes. I'm going to talk about a work that we did a little bit earlier than this, actually, but it was more fancy heights, and similar mathematics goes into it. For Falting's height and Néron-Tate height for higher cycles, we also had formulas and identities which also are computed tropically. So for the remainder of the time, I'm sorry I had promised that things just go strictly easier. It might be a bump now. I have to define two rather complicated heights, but then the final part of my talk is going to be, again, tropical computations and concrete formulas. And then, yeah. Let's see how much time I have. Let me not promise too much. So some more advanced heights. Falting's height and Néron-Tate. Néron-Tate is typically the same thing I've been talking about, the H hat D, but when I discussed that, it was height of a point. Now I want to talk about height of higher dimensional cycles. Okay. So again, A is the similar A over K is the abelian variety. Maybe I'm going to also fix a polarization. It's an abelian variety over K. I'm going to assume, for simplicity and not spending too much time, I'm going to assume K is large enough that you have so-called semi-abelian reduction. So K, this came up in the open problems session by Mikhail, that in fact the kind of things that he wants to compute are measuring how far a given K is from having this property. Then I already talked about Néron model, which was, so this is Néron model, which is, okay, I guess strictly speaking, I was talking in local situation, but you can write the same push-forward diagram and you have a Néron model over the ring of integers. So this is ring of integers. Then this morphism has a section. Remember, we are dealing with a abelian variety situation, which is a zero section. You can do the following. You can put a line bundle here, omega, which you pull back relative differentials And this is a vector bundle. You look at the determinant of that, because like Martin, I'm more comfortable with, or in number theory, line bundles have been used to compute degrees. So you get a line bundle on the base. And as Bingen correctly pointed out, I did say you want to compute degrees, but I never wrote down a degree. I'll do it now. So degree of this thing is faulting height. And remember, I didn't even use polarization yet. So stable faulting height, stable because I have semi-stable reduction, of A is defined to be degree of this omega. But I did say degree is a suspicious word here. This is affine, and you have to compactify in Arakelov world. So I put a hat here which encodes that Archimedean data that is needed to do this. There is a natural metric that you can put on the complex place here. It's called faulting's norm, I think. And for stability reasons, I'm going to remember the degree of the extension. Don't worry about that. But anyway, height equal to degree. That was my promise, and promise delivered. And I haven't really, and this was used by Faltings for his proof of Mordell. He wanted to show there are only finitely many abelian varieties in the moduli space satisfying certain things, certain properties, and this was kind of a Northcott phenomenon. You have this height on the moduli space, and you might want to show that there are only finitely many by bounding the height and something like that. Okay, so the definition is complicated. Just if you didn't follow, there is this real number that captures the complexity of your abelian variety and doesn't even look at the polarization. There is another real number, which is the Néron-Tate height. Of theta. So I have a principally polarized, I wanted to say, which I didn't say. This is principally polarized because I want to have a canonical theta function. Remember, you have a one-dimensional space of global sections for your line bundle. So you have a, well, up to some shift or something, you have a more or less well-defined theta divisor. It's not totally well-defined, but you can pick a symmetric effective from finitely many choices you have. It turns out what I'm going to define is not going to depend on this choice. And then now you have a kind of a, again, so theta, this is divisor for L, which is related to your polarization lambda. Then you put metric on this. So L hat is going to be L. And you put metric at every place according to the canonical process that I was talking about. For all places, you insist that the metric that you have should make that isomorphism into isometry. So L, let's say multiplication by 2. This should be isometry at every place. And you can do that. And then you compute another intersection number. I'll write it down, but don't worry about just like there. You can just read it as some intersection number that captures the complexity. Now it's complexity of A together with its polarization. Faulting height didn't need polarization. It's going to be some numbers, g factorial, g, k over q, and then some intersection products. So you have these enriched or meteorized line bundles. You can intersect them with themselves, restricted to theta, g copy. You do it g times in the Arakelov sense. So this is the Arakelov intersection. And you should trust me that the numbers are correct and the intersection theory exists, and you get a real number. And then people were wondering what is, first of all, how to compute this real number, and what is the connection with that other real number. So I'm going to give a couple of theorems. And in the case of Jacobians, it turns out that this function theta that I'm going to erase is going to come back again. Actually, for all abelian varieties, principal pairs abelian varieties, this function will come up. But in the case of Jacobians, you can even do graph theory to compute this number, the local contributions.
So, sorry, I have a question. The degree of omega is also equal to the self-intersection of this line model in this sense?
No, because that's 0, actually. If the top self-intersection of the line bundle on abelian variety is going to be 0. That's actually, that doesn't have this kind of, sorry, degree is top self-intersection of omega. I'm not doing it on the, yeah, this thing is top self-intersection of omega in the Oracle of sense. But it's not happening on the abelian variety. That's why I got confused. If you take, I don't even have a line bundle there to self-intersect. Okay. I have that omega. I don't have this L to self-intersect. I was saying this thing, if you just do G plus 1 times on A, you get 0. That's all I was saying. Sorry, I don't know who is talking. Can you raise your hand? Yes?
The far inclined there, is it a rational number?
It's not. It's real. Because the contribution from, if you do it over function fields, you have a hope, and in fact, perhaps true, that you get rational numbers. But the contribution from Archimedean place is highly transcendental, usually. OK, so the first theorem is, again, Chamberlain and plus Chamberlain Tuillier that I mentioned, plus Gubler, putting together, maybe plus epsilon, so Chamberlain. I'll just put some names, but it's not in one-to-one correspondence with papers. Maybe just putting them together is the epsilon part, which says there is a formula for this Néron-Tate height, which is kind of a summation over Berkovich spaces. Néron-Tate of theta. This is not about faulting side. It's some kind of a summation. Again, there is some 1 over degree of extension. G is the dimension. I apologize, I never wrote it down, but hopefully you have seen G enough. And then it's going to be some integral over the entire Berkovich space at every place of some function, which is actually the log of the section function that I already had in my first theorem, against d mu Monge-Ampere. So there's if you have a line bundle with a metric, there is a process that you can make a measure out of it, Monge-Ampere. But Gubler's contribution is that this Monge-Ampere actually is just Haar measure on the skeleton of the Berkovich space. And in the case of complex, it's just Haar measure on the complex torus. So that's a computation he did for Bogomolov conjecture. So there is a formula in terms of Berkovich spaces. And what I was just saying is that at least for non-Archimedean places, this is a statement about skeleton, right? But then I told you for the skeleton, I tell you what the function is. It's f trop. So we wrote this paper before the 2024 paper. In that paper, we don't have this remark, but now if you put them together, this is equal to, for V non-Archimedean, you actually know how to compute this. Haar measure on a real torus, and then you have what I called F-trop. And in the principally polarized case, you have a formula for it in terms of closest lattice point. In fact, if you use this over number fields to get rid of the Archimedean place, you can use this formula and very explicit computation to compute the Néron Tate height, which is rather unusual for higher dimensional cycles. But in particular, you can prove that this is a rational number. Remember, I said Néron Tate height is mysterious. Whenever it's not 0, we don't know what it is. But in the case of function fields, I'm saying you can prove that it's a rational number. And this type of argument happened in this work of a student of Yuan. Yang is the name?
Yes,
Yang, to prove that Néron Tate height of any cycle, not just theta, is going to be a rational number, essentially by the same argument, except since it's any cycle, he doesn't have F-trop formula. He should just abstractly argue that this number is always rational, and then you compute that. So that's a 2024 paper as well. OK. But let me now end with 2 theorems, which I've mentioned faulting site, but I haven't given any results about it. So my next 2 theorems are going to have names. Theorem A, which is the 4th theorem of the day. This is with de Jong. Which says the faulting height wants to be Néron Tate height. OK, so for some reason you have to put 2G, but we have been making weird normalization choices anyway. This shouldn't bother you. And in fact, this is, if I were over function field and I had no place of bad reduction, this is a Riemann-Roch phenomenon. This follows from Riemann-Roch. But if you don't have all those assumptions, it was known that they can't be the same. And in the case of good reduction, Jean-Benoit both had some results. And there's a history that I'm going to be very quick. I just want to recognize that this problem was studied in the past. And we weren't the first. But our contribution is, what if, in general case, what if you have bad reduction and you're over number field, what's going to happen? And our answer is essentially, there will be contributions from skeletons of Berkovich spaces that captures the discrepancy between the two. So there is the next thing is going to be some local contributions. And in particular, also by putting with the previous theorem, you get some kind of a sum over places here and sum over places here. You get the sum over places for faulting sites. So faulting site will also be decomposed into local contributions. OK, so I will be a little bit careless with some constants. You can find the exact quantities in the paper. So some I invariants coming from local places. My next job is to tell you what is the I invariant. There's a 2 here. That's why I had 2 different parentheses. And this is the size of the residue field. I would say don't worry too much about the normalizations and these constants. The main thing you should wonder now, what is this I that I'm talking about? So each Berkovich space will give you an I. And the infinite place also will give you an I, which is some integral. I won't spend time on that. But the tropical contribution is this I. And that's, in the case of Jacobian, relate to electrical networks as well. So you will have a formula for faulting height where, in the case of Jacobians, is via electrical networks. So what is I? So remember, we have this theta function. Recall. You have this closest point function to closest lattice point function. This is a function on the skeleton. Skeleton also has, so this is the skeleton at place V. Skeleton also has Haar measure. It's a group. So once so there is a natural measure on this torus, real torus. I'm going to, I have to fix some constants. I'm going to say that the volume of the entire torus is 1. That fixes my Haar measure. And I, at that place, will be the integral over sigma of this function. So it's kind of, I would call it second moment of the torus, because this is kind of a quadratic function. So I'm looking at some kind of x squared over and take an integration. So it's second moment. And as such, actually, this I has been studied for practical reasons. Remember, I was quantizing my data. Vector space was data. Lattice points were my digital stuff. And that was the error. How far am I from the actual data? This is the average. This is the mean squared error, if you think of it that way. So I'm saying at every place you have a mean squared error that you should plug in here. And that's the theorem. I'm going to end by saying that this can be very much computed. So as Bingyang was saying yesterday, pretty much any lattice problem is impossibly difficult. The first question is, can you compute this? It's expected this computation is very difficult, more than NP hard. It's supposed to be sharp P hard. In fact, there were attempts to try to prove that this I, even for the Jacobian that I care about, is difficult. They weren't saying the word Jacobian, but they were looking at lattices coming from graphs. And I'm going to say that there is a way to compute, so theorem B, again with de Jong, is that I of Jacobian of a graph, which remember, it's the skeleton of the Jacobian of the curve, right? So in the case of Jacobians, the I of a real torus sitting inside Berkovich space, which is what I want, is going to be 1/8 L of the graph minus 1/2 tau of the graph. What is L of the graph and tau of the graph? L is super easy. It's just the total length of the graph. Tau is very much potential theoretic. It's actually a certain capacity that you can put on graphs. And the last theorem I'm going to say is how to write down tau, which is very computable. You can compute it, in fact, by combinatorial Laplacian stuff, which means that you can compute this thing. So the upshot at the end, when I'm rushing, is that I, for the case of Jacobians, has a concrete efficient formula that is very linear algebraic. And I should say that I still expect for general abelian varieties, I should be difficult because any lattice pretty much can appear. And I still expect computer scientists are right that this is a hard to compute quantity. But maybe as an open problem for prim varieties for some of the people in this room, this might be computable. But I know someone is working on it, so I didn't want to put it on the board yesterday. So please let me know if you want to think about it, and I'll connect you with people that are interested. But pick your favorite type of abelian variety and see if you can compute these things. In fact, I challenge you to compute this I in the case of the lattice that I had on the board. So if you have this graph, you will get a triangular lattice. So exercise, it's a mean exercise for a calculus student. Compute I. It's just multivariable calculus, integrating a quadratic function, but the domain that you will end up integrating is weird. But OK, the last theorem. So in the form that I'm going to describe is, again, our work. But certainly, there was a student of Bob Romley that studied the tau invariant in great detail, and there are beautiful problems about that. So in equivalent form, Zubair-Schinker. I apologize, I don't know how to write the correct letters in Turkish. Earlier than us had an equivalent formula. Namely, tau. The difficult theorem in our paper is this identity, and I can tell you more afterwards why we suffered so much. But the reason that we came up with this identity was actually coming from a Riemann surface identity due to Robert Wilms, and we sort of guessed what the limit should be when you go to tropical limits. And then we had to only prove it, but with new techniques, combinatorial proof. So tau is 1/12 summation over edges. So if you have a graph, you can just pick a bunch of vertices and pick up your edges. And then you have 1 minus effective resistance across the edge divided by the length of the edge squared times length of the edge plus 1/4 summation again over edges, effective resistance across that edge with a base point Q minus with the base point Q squared divided by length of E. Q is arbitrary, any vertex, any point. So it's actually not totally obvious why this formula, this doesn't depend on a Q, but this depends on Q. Yeah, I don't want you to dwell on how this is done, just it's a computable formula in terms of effective resistances that I said before. And I just realized I didn't say what tau, definition of tau is the theorem. There is a definition where this is the theorem. So the definition of tau is maximum of some double integral there's a 1/2 somewhere. So over all measures of mass 1, there is a unique measure maximizing this double integral, which you, for good reasons, you might want to call it capacity of the graph with respect to this kernel effective resistance. This definition existed in the literature due to Romley, again, a number theorist in the context of non-Archimedean potential theory. So the theorem is that this mysterious quantity is very much computable. Not a deep theorem. This is difficult theorem, but the motivation is also the height of Néron-Tate versus faultings. And that's all I had to say. Thank you.